near the free edge on the composite. So to begin with, I will divide my talk into several parts. So I will start with the problem statement, then go to research objectives, talk about the finite element modeling, and then the results. So the people who work with composites, I mean mostly with the production of the details from composite, they face with a problem of residual stress that causes the shape distortions, bare page, fiber and tone misalignment, and what's more important, the transverse cracking and illumination. So this effect is more visual for the composites that are quite thick. So up to date, there is no an effective and expensive method to analyze these residual stresses and to take into assumption when you study the composite under loading. So it's a nice thing that the composites, speaking in common, they are not like in metals. So if in metals we can relax, provide the relaxation of the residual stresses, in composites it's not so. You should think about this problem on this stage of the design of the composite team. So the research objectives. So I will start from the development of modeling technique that give the opportunity to predict the stress strain distribution in composite detail, then determine the values of residual stress in composite sample, so of the material mentioned in the presentation. Then determine the change in residual stress in composite near the free edge after cutout into two parts, and then I will compare the damage distribution near the free edge with the presence of these residual stresses in case of uniaxial loading. So let's start. So the material model is quite well known. So this model takes into account the chemical and physical things that appear in composite during the polymerization. So the problem of residual stresses, it comes because of different properties in transverse and in longitudinal directions. So this model was implemented in Abacus by writing the user material model. So it was verified on the sample with 0 and 90 layup, because for this sample this effect is more visible because we have the most different values. So then for the simulation, so firstly we verified our model, and now let's start our investigation of the stresses near the free edge. So the sample that was taken into the analysis, it's like this, of very simple form. So the layout is 0.90. The thickness is 3 millimeters, about 3 millimeters. Here it's the cycle of the polymerization that is recommended by the manufacturer. So let's take some assumptions for our modeling. So we'll model and consider the two D-plane strain formulation to the symmetry of the layup. Then we'll not take into consideration the influence of the mold because the form is quite simple. And then we assume that the cutout is ideal. So we created the mesh. We have the parse mesh here, and in the zone of the cutout it's quite finite because in other way we will not catch the effect. What's important, we use the square elements near the notch. So to simulate this thing in Abacus, we decided to to go to the local, from global to local system coordinate. So here you can see this is like the global of the sample, and this is local for layers of 0 and 90. And here we can see how the stresses in local and global coordinate system are defined. So the analysis provided in 2 steps. In the first step, we polymerize our sample using our created model that was implemented in the code. Then we model the cutout, and then after that we, if we want to understand how the sample behaves under uniaxial loading with residual stress, we model this loading. So now we'll go to the study of the effect of residual stresses in the sample after cutout. So here we can see that the stress distribution in the sample before cut and after cut. You see that the stresses, they change. Here we can see that actually the results are mesh dependent. That's why we need to create quite small elements. And so it should be, you see that these stresses are mesh dependent, and if we take, for example, 2 elements per layer, we can get some wrong results. So this is the effect of residual stress on total stress after cutout. So it shows how it changes and what's important to mention. So that the stresses in local, so I'm talking about the stresses in local system. So they are quite close to the ultimate stress. So this stress, so if we look at the data provided by the manufacturer, we see that the stress is quite close to the ultimate stress of the matrix. So it seems that with the quite small loading, we can get some cracks and some defects in the composite. So, and that's why we can't ignore it. So now let's study the stress strain state in specimen during uniaxial loading. We'll provide the loading in so in this way, on the picture we can see our specimen. So they lay up just the same that was used for polymerization. Here is the result of the model of the loading without residual stresses. So we see that the matrix is completely cracked, and here with the residual stresses. It should be mentioned that for modeling this uniaxial loading and the fracture, so the specific model was implemented that was developed by Dr. Fedulov, and this is like the updated model of Zinoviev. So, and what we got that we have not only transverse cracking of the matrix under loading, but we also can see the cracks in matrix along the fibers in the direction of loading. So, and this is quite similar to results that were mentioned in the articles. So it seems that this model is quite good in describing the process that come in composites. So here, the small video of the damaging. We load our sample. So here we can see the cracks that come along the direction of the fibers that I mentioned before. And so you see that even after you cut out, it's the stress grows. The maximum stress after cut out are concentrated in a small area, so the area is about 10 microns. The possible failure mechanism of composite is matrix mode fail. So I mentioned that the stresses are close to the ultimate stress of the matrix. And so this is not connected with the shift of the layers. And the described effect can be seen on the shell elements by modeling, so they're only in 3D. The value of stress immediately changes with the increasing of number of elements. So I showed that it depends on the size of the elements and the number of the elements per layer. So these minimum elements should be taken to account to get the adequate result. So to sum up, this model is quite universal, and you can applicate it for any kind of material if you know the properties, and you can also update some models like them when you study the failure of the composites.